Good morning, everyone. So I'm the moderator of this session. Some housekeeping rules. We won't have time to ask questions, but these questions can be asked, as Peter said, when you visit the posters. Perhaps I can already welcome the first speaker on the floor, and that's Javier Gracia-Tabuenca. He originally is from Spain, stayed in Finland after his PhD to work for the FinGen project. FinGen was the first in Finland to adopt OMOP 3 years ago, and today they have 4 OMOP databases from hospitals and registries, and they have created the FinOMOP group. Please come to the floor.
Okay, hello everyone. So I will try to answer a question that has appeared a couple of times. So let's imagine that you are building your common data model, and then you find that some of the vocabularies you have, they don't exist into Athena. So currently there is 2 things you can do. One is to contact the vocabulary working group and ask them to put that new vocabulary there. And that's really good because then it can be accessed by everybody. You know, they have some quality checks. And then you know that your codes will appear in Atlas and you can play with them. Maybe a limitation of that is that it might take some time, especially you are doing errors in your mappings and you want to fix them. Maybe it takes some time that you see that reflected into your database. The other option is that you can populate this source to concept map table. Whatever change you do there is going to be immediately seen in your database, but then you lose all those nice properties. And especially, that's only visible to you. So maybe there's other people that is interested in the same vocabulary, but they just don't know you are working on that. So I will show, we have done in Finland, something in between. The way we do in Finland we have these 4 different databases. And we have created this FinOMOP group where, among other things, one of the important things we do is we are building or mapping the local vocabularies together for use of everybody. So the way we do this is we have created this GitHub repository where we have for each of the local vocabularies, we have the Usagi file plus other files with information. We have made some R tool that is transforming those into the OMOP vocabulary tables like concept relationship and so on. Then the tool can take those and join them with the tables you get from Athena. So then you end up with a group of tables that contains both the international and national vocabularies. And you can just get those tables directly into your ETL. But then we went a bit further, and we have also added to this GitHub repository some record counts. So each of the databases has uploaded a file where you have all the local codes and how many times that code appears in the database, so that we can create this status dashboard where we can see for each of these local vocabularies not only how many of the codes have been mapped, but also how well do they cover the events in each database. Because you might know that many times just mapping the top 30% of the codes in your national vocabulary is enough to cover 80–90% of the events in the database. So we want to be sure that that applies to all the participant databases. Finally, because we have this in GitHub, we can also treat this as a software development. So we can have this development branch. And then if anybody of the databases or participants wants to make a change, they want to add a new vocabulary, they want to add new mappings, they want to fix an error, they can just create a feature branch, work there, do any change they want, do any error they want. And when they are ready, they can make a pull request. This pull request automatically will create this status dashboard, so the repo maintainer can check if everything is okay. And if so, it can be merged to development. This can continue and adding more features and improvements until every now and then we can just decide that we make a release and everybody in Finland will synchronize to the same set of vocabularies. So finally, you are a Nordic country. Maybe you can just check. We have this status dashboard that is public, so maybe you can check if some of the vocabularies is also useful for you. And we can work on them together in this system or just move them to Athena. That's okay. We have done also some demo repository here. So if you since this problem is familiar to you, you can just clone that and adapt it. You can also see the art tools there, and then just come to see me to the poster. But actually, we have now a software demonstration, so you can just come there. It was some error we made. So come there to see us. Yeah, thanks.
Thank you. Thank you very much for this nice presentation. And we have sessions where we go from the mapping, the methods, and then the clinical implementation, which is great in this session. Next speaker is Jared Houghtaling. Perhaps you can already come to the floor. You have a background in disease diagnostics, protein characterization, and signal processing. You received your PhD in biomedical engineering from University of Michigan. Jared is currently a lead data scientist at EHDEN Study-A-Thon, where he has led a number of OMOP data harmonization efforts, both within Europe and beyond, and you're going to show the experience you had in Rwanda. Thank you.
Great, thanks for the nice introduction. It's very exciting to be here presenting this work to you all today. And the work that I'm going to be presenting in particular is on the LISTAR project, which has too long of a name for me to say it in this 5 minutes, but briefly, we're trying to harmonize data for these 16 different OMOP data sources around the country into an OMOP data sources, into a federated network that then we can leverage various artificial intelligence and machine learning techniques to extract insights, and in particular related to COVID. I want to give a quick shout out to Micah, who did a very nice job of explaining the whole setup of a federated network and the steps that you need to go through. I will focus in particular on the ETL and the quality control feedback steps that we implemented in this particular network. So just a bit of background to get you primed. This project is a collaboration between the University of Ghent in Belgium, University of Rwanda in Kigali, the Biomedical Center in Kigali, the Rwandan Ministry of Health, and the company where I work, Eden's Health, here in Belgium. And it initially was focused on tracking COVID response and really public health response to COVID. It has since expanded to other disease areas as there's been kind of an acknowledgement of, hey, this is a pretty rich data set, we can do a lot more here. And the map kind of shows you really the geographic diversity that we have captured in this network. And one maybe other quick point, these hospitals that are participating, they have one of two open source EHR systems, so either Open Clinic GA or Open MRS. And so we were able to reuse most of our transformation components across the various hospitals, which made things much more efficient in terms of mapping all of this. For the technical ones out there, this is kind of the setup that we deployed at each of our sites. What we ended up doing was putting Docker on a bunch of different Mac minis, so the little box with running Mac OS, and then installing various services on those machines and shipping them to Rwanda where they were set up at the hospitals. And I'll just go quickly around, starting at the top in kind of a counterclockwise fashion, but we have the ETL processes that then extract the source data from the MySQL database in the EHR system that then is converted by our ETL process into OMOP, into the central Postgres database, where it also reaches out to a kind of a federated COVID data set and kind of brings in some of that COVID information to each data site. We then have Atlas and Web API available for each of our sites to go in and look at cohorts and do some data exploration. We have RStudio with all the Hades packages installed to do, again, additional OHDSI work there. Down at the bottom, which is kind of the focus today, is Aries Indexer, as well as the data quality dashboard and Achilles to run your data quality checks on the OMOP data that comes out of this. And then in the bottom right, we got a lot of questions regarding reporting obligations. So each of these hospitals needs to report their data to the Ministry of Health. And we have helped them also with the help of Peter Reinbeck's CDM inspection package. We kind of modified that to make a report generator for Rwanda that then has a shiny application interface to generate these kind of specific monthly reports that they needed. And then on top of all of that, we have Arachne, which shout out to the Odysseus team. We've done some work kind of customizing that for this particular deployment, and that allows this federated structure of deploying things remotely and setting up federated studies. Last slide here. The actual quality feedback loop, we have our ETL that we execute on each of the Mac minis. That ETL we can deploy using a simple a simple MDM framework, so it's a multi-device management thing where we can execute shell scripts. And then that ETL produces, of course, an OMOP output, which then we can run Ares Indexer and our quality checks on. Those Ares Indexer results get posted back to this central location hosted by the Ministry of Health, where then they can be visualized in the context of all of the other data sources and sites in terms of what quality do we have where. And again, the source EHR step of this, where we're actually pulling stuff out of the MySQL database, we're still in the process of automating that step, but everything else here we can do from Belgium, essentially, across the network. And so where are we at now? This is as of, I think, a couple weeks ago. We have 14 out of the 16 sources into OMOP at this point. More than 3 million patients are represented, unique patients, and that is approximately 25% of the Rwandan population, which is quite a nice milestone to hit. You can see that there are data quality issues, but that's, again, this process of iteratively improving our ETLs and improving our mappings to get better data quality across the network so that we can run some exciting studies, hopefully in the future, and then present them next year here in Rotterdam. So all of this work would not have been possible without the help of a massive team and some fantastic people. I'd like to acknowledge Ben Burke in particular, who helped with a lot of the infrastructure, but also Laura, Frederick, Ivo, and Anne on the EHDEN's Health team, as well as all of the enthusiastic data managers at the sites across Rwanda, and some very key people at the Rwanda Biomedical Center, as well as the funding agencies, so Canada's International Development Research Center and the Swedish International Development Cooperation Agency funded this work. Thank you very much for your time, and I'm happy to discuss more at the poster.
Thank you, Jared, for a great presentation, great initiative. Good to have data from Africa on board as well. Next speaker is Markus Haug from Estonia. He's a doctoral student in health informatics at the University of Tartu, Estonia, and he specializes in modeling patient treatment trajectories.
So thank you for the introduction, and hello by me. In the next 5 minutes, we're going to run through 2 packages I have developed and the networks that I am running through, so hold on. Well, let's suppose that you're me and you are interested in heart failure patients. Heart failure has had its standard of care for many years, and now we have been introduced some new evidence that telemonitoring could enhance their treatment. With the new treatment, there comes extra costs, but maybe the quality of the patients, the quality of the healthcare, the quality of their life would be better before they die or in the time of treatment. And for that, we will model the patients, giving the full spectrum of their treatment we're going to cover with different states. First of all, heart failure 0, which means the patient had 0 hospitalizations in the last year, and then onward heart failure 1, heart failure 2, and heart failure 3+, meaning the patient had 3 or more heart failure-related hospitalizations in the past year. And then, of course, the death. From the graph, we can see that the alternative care costs more, but the quality of life of the patient is better. And for determining whether or not the telemonitoring is feasible, we can do cost-effectiveness analysis, and for that we need 3 main components, which we can learn from observational data. First of all, we need a transitional matrix between the states. Well, from the matrix you can see that a patient which has been in the heart failure 3 state has a probability of 7 dying in the next month. We can also learn initial distribution for doing the analysis and also the costs of different states. And for running such analysis, we propose a new workflow. Of course, we all know about Atlas, about OMOP CDM, and if we think about cohorts as states, we can generate patient treatment trajectories using a tool called cohort 2 trajectory. After using this, the output of this package, we can use the package trajectory Markov analysis, which could use the output of cohort 2 trajectory or other trajectories generated by any tool or any database for creating discrete or continuous Markov models. We can learn treatment cost data and also generate synthetic treatment trajectories. And after that, by combining those two packages, we can conduct pretty much any workflow, any network study for such questions. And so a brief overview of the network study we have run. So far, we have had 5 different data sets contributing, 2 from Estonia, 1 from Spain, 1 from the USA, Columbia University, and one from Serbia. Maybe the first and most important insight is that you really gotta mind the source of your data, because from the initial distributions here, you might see that Estonia and Spain have pretty similar distributions, but the data sets from USA and Serbia are a bit different. This is explainable because they're hospital data sets, and a lot of persons who were admitted to the hospital died within the first month. But now to the conclusion. When learning the models and simulating the treatments, we learned that telemonitoring is not feasible. This is because of the rate of ICR, a metric for comparing how much it costs to how much helpful it is. And this is a rate against quality-adjusted life year. For example, in Estonia, we are ready to pay 40,000 euros per quali, and as you can see from the results, that pretty much none of the data sets gave us the evidence that one quali could be less than 40,000 euros. And therefore, we conducted analysis and understood that telemonitoring is not feasible to use in our healthcare system setting. I'd like to give a quick shout out to my team from Tartu, Estonia, and also thank all of the data partners. If you have any more questions, you can come to Poster 88, and you can join the study as well. It's still open until the end of July. Thank you.
Thank you, Markus, for your great presentation and considering also the costs of healthcare. So that's very, very important, of course. Next speaker is Henrik John from Department of Medical Informatics, colleague of mine. He's a student, PhD student at our department, and he focuses on methodological research for clinical prediction modeling, and you're working on several projects in OHDSI and EHDEN.
Yes. Yeah, thank you, Katia. Deep learning comparison is an OHDSI network study that we're currently working on, in which we compare what we call a conventional prediction method or model to the more advanced and more complex deep learning methods. And basically what we found is that in this domain of clinical prediction modeling, by far the most popular group of models are these conventional models. So logistic regression, Cox regression, decision trees, but also the ensemble methods like gradient boosting or random forest. And that is actually quite contrary to other domains. Take, for example, anything vision related or image recognition related, where these deep learning methods are actually much more prevalent. And there's a reason for that, and there are a couple of papers. And basically, deep learning was found to not really work very well on observational healthcare data, and in particular here, tabular data, because this data is too sparse, too high dimensional, and there's a lot of heterogeneity. So across databases, of course, but then even in a single database, think, for example, of a GP database where the data is coming from different practices. You'll have a lot of heterogeneity. So we'll be comparing logistic regression, L1 regularized. So this is our, at the moment, I think, the go-to method for clinical prediction modeling, to gradient boosting, another method that we say is conventional. Both these methods actually show really good performance on very sparse data, and the gradient boosting also had some good results on continuous data, discrete data, so in general a bit denser data. And in addition should be able to model some nonlinear effects. Then we have the ResNet. The ResNet was actually popularized a couple of years ago, mainly used in combination with convolutional layers, where it was used for, well, really for any vision and imaging tasks. And technically, it's a bit of an evolution of the standard neural network, so the multi-layer perceptron, which introduces these skip connections between the layers to deal with the vanishing gradient problem that you get when you try to build like deeper and deeper networks. And then we have the transformer, which is probably at the moment the state-of-the-art model for deep learning. It uses an attention mechanism for the feature selection, and this one also has an embedding layer in the front, which the authors call a FT for feature tokenizer. So both these deep learning models are actually optimized for tabular data. We'll be predicting dementia in persons aged 55 and above, lung cancer in persons aged 45 and above, and then also the transition of persons that are initially diagnosed with major depressive disorder, but then go on to get a new diagnosis of bipolar disorder. And we have a couple confirmed databases, the US-American Optum, claims, and EHR databases, the Dutch IPSI-GP database, and then we have the Korean AOSOM EHR database. And a couple of results are in as well for the dementia and lung cancer cohorts for IPSI and AOSOM. And for the moment, at least, what we see is that the models, they seem to perform very much the same. In fact, the logistic regression model seems to outperform, especially on AOSOM, the other methods. And if you have a very complex model like a transformer and then a very simple model like a logistic regression model, and they perform kind of the same when you look at the discrimination, then generally the choice would be for the simpler model, because it will be, first of all, faster to train. It has fewer parameters. It will be probably easier to implement in clinical practice, or in general transport and externally validate, and then probably also easier to interpret. Well, we have a couple of blanks here. This is why, because this is an ongoing study. So I'd like to invite you, if you're interested, to join the study at this study repository. There's just one requirement, is that you will need a GPU to run this. Otherwise, the deep learning models will take an unreasonable amount of time to fit. And yeah, help us assess the added value of observational data for the development of deep learning models. Thanks.
Thank you for a great presentation. Looking forward to the results, and also if other data sources join. Next speaker is Ian Wong from University of Hong Kong. We worked together in the past, Ian. You're co-director of the Center for Safe Medication Practice and Research, Department of Pharmacology and Pharmacy, and you're co-director of the Center for Medication Optimization Research and Education at University College London Hospital and UCL School of Pharmacy. Your experience or expertise is in using big data research to investigate safety and optimum use of medications for a variety of conditions.
It's so good to see you, Katia. And so, you know, Patrick is always my hero. So I learned something from Patrick this morning. So who do you have the database that you can contribute to study? Please stand up now. No one? Oh, come on. Sure.
After your talk.
Okay. So basically, for this particular talk, we are going to use the very simple method. We're looking into the COVID-19 infection and associated with a range of cardiovascular disease looking into sort of like the short-term, medium-term, and also the long-term sequelae after the infection. So the study design, again, is quite simple, retrospective study, cohort study, using propensity score matching. The study population, of course, we're comparing the people that with the COVID-19 infection and the people without in a certain period of time, December 1st of 2019 to 20, and then the long COVID-19 controls. The study outcome that we're specifically interested in the cardiovascular side of it. And then the follow-up, we have short-term, up to 6 months, and then the medium-term, 6 months to 1 year, and then the last bit is 1 to 3 years. And of course, you can see that the project is ongoing. So there are some preliminary data in here. I think it's quite common that the raw analysis and then the adjusted analysis, you can see the calibrated hazard ratio is actually moved it towards the one. So that's a continuous to looking into having more data that we would like to have. One of the important points is I found out that this is the 4th study that we run in OHDSI. One of the biggest challenge in the OHDSI study for me to run it is actually have the data custodian, the owner, to actually join the study. And that's one of the reasons why I would like to ask the question is, how many of you sitting here actually have data? So at the beginning, if I ask you, you stand up. And since no one actually stand up, let me ask again, how many of you actually have data, can contribute to the study? Please stand up. Would you like to join the study? Oh, come on, join the study, stand up. At least I know right now I have some more people. Okay, I give you an opportunity. Just contact me if you want to join the study. We actually have quite a few of those studies ongoing because the Hong Kong government is sponsoring quite a lot of those studies. Would like to know the long-term consequence of it because we were hit by SARS 20 years ago, and we're still dealing with the issue created by SARS 20 years ago. So that would be something that we are really interested in. So thank you very much.
Thank you, Ian. And you had some data sources, so I mean that's good. Huh? They will pop by. Next speaker is Judith Brand from the Uppsala Monitoring Center in Sweden. She's an epidemiologist by training. She worked with observational health data for several years before joining the Uppsala Monitoring Center and before entering the field of pharmacovigilance. And your main research interest is in integrating evidence from different data sources and methodologies to strengthen causal inference. Thank you.
Thank you, Katia, and hello, everyone. I'm delighted to be here. So I will talk about how data from the network can help us to identify potential adverse drug reactions or signals. And more specifically, the lessons that we learned from last year's Study-A-Thon that we organized together with partners from EHDEN. So how do we identify signals at the Uppsala Monitoring Center? Well, our starting point is Vigibase, which is the WHO global database of individual case safety reports of suspected adverse drug reactions. And because of the size of the database, now containing over 34 million reports and capturing over 4 million drug event combinations, it's impossible for us to screen for signals on a case-by-case basis. So instead, we use a statistical algorithm to prioritize signals for expert human review. And these prioritized statistical signals then undergo a step which we call validation, which is an initial assessment during which a team of our signal assessors evaluates the signals in terms of strength of evidence, the potential public health and clinical impact, and also whether the signal is known or not to determine if further assessment is needed. And for this, our signal assessors uses information from Vigibase, but also we've used regulatory documents and the literature. And it's often, usually takes place in a fairly short period of time, so only a couple of hours at the most for each signal. The signals that pass the stage then undergo assessment, And this is a more time-consuming step because this involved the in-depth clinical assessment of the case reports of a signal, as well as more in-depth literature review. Now, as you can see in this process, signal validation is quite a critical step because it's the first instance that a signal undergoes human review, and it's also kind of a gatekeeper for the assessment. However, this step is also quite challenging because often the information available is not sufficient for making informed decisions. Routine health data are typically used in our context later on to evaluate communicated signals, but we think that they can also provide relevant contextual information to support signal validation, and this is what we wanted to explore during the study-a-thon. So what did we do? Well, we selected statistical signals that involved a generic drug and a reported adverse event term mapped to one of the 16 phenotypes that have been developed by OHDSI for the research on COVID-19 vaccines. And then what we did is that we basically did signal validation as usual, but with the only difference being that the signal assessors could now ask specific questions regarding the signal that they could not answer using the regular sources of information to an analytics team of OHDSI experts. And this team then translated these questions into scripts, which were executed by 10 data partners who participated during the study-a-thon and then returned their relevant findings to the signal validation team. So all the analyses were designed on the fly, and they were mainly executed in Atlas, and they focus on characterization. So to contextualize the drug, the indication for drug use, or the adverse event, depending on the question from the signal assessor. So what did we learn? First of all, that this is feasible, that we can do it. Because thanks to the infrastructure and the analytical tools that are available in the network, it only took us a couple of hours to design the analysis, to execution and interpretation of the results for each signal. Then also very important is that we saw that the routine health data really could support the signal validation because 5 out of the 8 statistical signals were informed by the data. And for these signals, the data helped the signal assessors to understand potential confounding and bias, and also the potential public health and clinical impact. And then in terms of prioritization, I think a bonus was that by integrating the routine health data very early on in the process, we could basically see if it was possible to assess a signal further in a pharmacoepi study. Apart from these insights, we also defined some key user requirements for future implementation of these data in our routine signal validation process. So first of all, what is key is that you need a multidisciplinary team, that you also need to have access to a large and diverse data network, because during the study-a-thon, we saw that some of the questions could not be addressed in the data available, but could have been addressed in the bigger network. In terms of phenotypes, because in pharmacovigilance we work with a lot of different adverse events, it's important to have a wide range of phenotypes for adverse events, and also an effective bridge between our source vocabulary in Vigibase and the OMOP CDM. And then in terms of the analysis, during the study-a-thons, they were specifically tailored to the questions of the signal assessors, but we realized that many of the analyses were useful to address questions for any type of signal. So we really would recommend a more like a systematic approach with a standard set of analysis that could then also be pre-computed, so the process would be become more efficient. And then lastly, because we work on the significant time pressures, data governance to support the pharmacovigilance use case is important. If you would like to learn more, please come and visit our poster. And last but not least, I would also like to take this opportunity to thank everyone who made this study-a-thon happen. Thank you.
Thank you, Judith. It's great to see the bridge to pharmacovigilance data as well. Next speaker is Marti Catala Sabate from University of Oxford. He's a senior data scientist in the Pharmaco and Device Epidemiology Group at University of Oxford, highly involved in developing of new packages within the Darwin EU network, and you're presenting on behalf of Kim Lopez-Guel, who couldn't make it because of traveling issues, I think.
Yep. Thank you, Katia. As Katia said, I'm presenting on behalf of Kim, who couldn't make it. What I'm going to present, I have 5 minutes to present. Basically, if you remember before, 1 hour ago, Carlos was presenting the EHDEN Study-A-Thon, and he skipped 2 slides very fast, saying that it was not interesting for his slides. So that's what I'm going to present. So now it's interesting. Basically, I'm going to present the pattern of long COVID symptoms and conditions. Basically, it's a clustering analysis based in multiple databases in the EHDEN network. It was the results of the Study-A-Thon, as I was saying, so lots and lots of people were involved. Most of them I can see today in the audience. Maybe highlight Kim and Annika, who lead to move forward this project. So first of all, which is the motivation? At the beginning of the pandemic, as you all know, we were focused in hospitals, prediction of new cases, characterizing the acute disease, and so more after some time, we realized that there were more things about COVID that we could learn, for example, the long-term complications. And we saw that around 10% of the people who developed COVID, they presented some complications. Here are the results of a nice review meta-analysis that I found. There are lots of symptoms that they were reported across the whole body, and there was not a clear pattern. Yeah, maybe we can see that 58% develop fatigue, but we can see lots of different symptoms across the whole body. So then the World Health Organization came and said, okay, long COVID is these 25 symptoms that we identified, and any of these 25 symptoms after 3 months after the COVID PCR positive test, so that's a long COVID. So what's going to be our definition for this Study-A-Thon and how we work it? We define a long COVID as first a diagnosis of or a positive test, then one of these 25 symptoms present at least 3 months after, and that this symptom was not present before the PCR test. So we had 3 objectives during the Study-A-Thon. The first one was to describe the epidemiology of long COVID. Here, Frank has a very nice poster on number 75. Then we had a second objective that was to characterize the populations of long COVID. We had a very nice shiny app. We worked to characterize all the different individuals who presented different symptoms and so. And what I'm presenting today, there is this objective 3, that it was to identify the long COVID subgroups. So as said before, this was conducted in a Study-A-Thon in Oxford, where 13 data partners from EHDEN from 9 different countries participated. And yeah. So now I'm going to present briefly which were the results of this clustering. It was a latent class analysis. Here we can see the results for the one where we clustered individuals who presented at least one of these 25 symptoms. And on the left, we can see the results from CPRD Gold. We can see that there are some clusters that make clinical sense, and we see the anxiety plus depression. we also see like a cluster that is like people who only presented one symptom, that in this case is joint pain. And then we said, okay, now we have to compare like across different databases. Like these clusters are consistent. And then, by the way, thank you very much. I don't know if Raivo is here, but thank you very much for the nice plot. And here we can see like the comparison across different databases. And what we saw is that there were some symptoms like anxiety that like they were present in more of one database, or depression. But then we saw like in CPRD Gold, we have a clear cluster that it's joint pain. So, and CPRD Gold is the only database who was presenting it. So we saw that there were some, or also fatigue, some clusters that were presented in only one database, and most of these clusters only presented one symptom. So there was like loss of heterogeneity. So we did like a subsequent analysis that it was like, okay, let's restrict to individuals who at least have 3 of these symptoms. And then there we saw like more clinical relevant stuff. Like for example, these are again the results for CPRD Gold. And then we see that we observed like 4 different clusters. The first one was headache-related issues. Second one was gastrointestinal issues. And we have a third one that was anxiety plus depression. And again, we compared these results across like different databases. And what we saw, and here like you have to believe me, but because I couldn't like write like different animations, but we've seen that there are like basically three patterns, 3 clusters that are reproduced across like nearly all the databases that are like the anxiety plus depression, the dyspnea and cough, and the gastrointestinal issues. So yeah, with this, thank you very much for your attention. If you want more information, you can contact Kim. If you contact her, like just say that I presented this very well, and it was a very nice presentation. And yeah, thank to everyone who participated.
Marti, and you presented very well, so I'll tell her. Next speaker is Alex Rekkas, a colleague of me as well, a PhD candidate at our department. Before starting his PhD, he obtained a Bachelor of Science in Mathematics from the Aristotle University of Thessaloniki in Greece, and you have a Master of Science in Statistics from the Catholic University of Leuven, and your current research interest focuses on predictive approaches for the assessment of treatment effect heterogeneity. The floor is yours.
Thanks, Katia. So hello, everyone. I'm going to be presenting some very early results of our analysis for the evaluation of treatment effect heterogeneity in the LEGEND-Hypertension study. So we do this analysis using a recently proposed standardized framework for the evaluation of treatment effect heterogeneity in large observational databases using a risk-based approach. So this framework is applied in 5 separate steps. So in the first step, we define the problem at hand. To do that, we're required to define at least 3 separate cohorts. So we need we need 1 treatment cohort, 1 comparator cohort, and 1 or more outcome cohorts. So for the second step, we need to identify the relevant databases and from which we will extract the patients using cohort definitions from the previous step. In the third step, we define prediction models for predicting the outcome risk for 1 or more outcomes of interest. We do so by pooling the treatment and comparator cohorts into a single target cohort, and then we use the patient-level prediction package to develop prediction models using one of the available model options that we have there. And once we do that, in the fourth step, we stratify the population into risk strata of predicted risk. And within risk strata, we develop separate propensity score models. And then within this risk strata, again, we evaluate several diagnostics that are very common to the OHDSI approaches. So we evaluate covariate balance before and after a propensity score adjustment. We evaluate the degree of overlap between preference score distributions, and we also carry out negative control analysis. to evaluate the presence of any, the evidence for presence of any unobserved confounding. And if we pass all these diagnostics, then we can proceed with evaluating treatment effects, both on the relative and the absolute scale, within the risk strata again. And in the final step, we combine the results and we summarize. At this stage, we only have generated the results from 2 US claims databases, namely the IBM MarketScan multi-state Medicaid database, that's here MDCD, and the IBM MarketScan claims database, here it's CCAE. So we see in the table that we have adequate numbers of patients for all cohorts, for all treatment cohorts, except maybe for the case of non-dehydropyridine calcium channel blockers in MDCT, we have a little bit less patient, but we'll see how this goes. So here we stratify patients on the predicted acute myocardial infarction risk. And that is, we separate patients into patients below 1%, patients between 1 and 1.5%, and patients above 1.5% acute 2-year acute myocardial infarction risk. Then again, we separate patients in risk strata, and then within risk strata we evaluate again like the standard diagnosis that I said before, and then we estimate relative treatment effects using Cox regression, and the absolute treatment effects from the difference between the Kaplan-Meier estimates at 2 years after treatment initiation. Yeah, so here I plotted some results some results on the absolute scale for the comparison of thiazides to the other 4 drug classes for the outcome of acute myocardial infarction. So on this side, we see an increasing pattern for benefits with thiazide with increasing acute myocardial infarction risk. However, on the other side, we don't see that, so we don't see any pattern. This can mainly be attributed to the fact that patients in CCAE tend to be younger and healthier. In this way, they end up in the lower risk category, and thus we only have results for this lower risk category. Still, this is this is still useful for us because we can say this provides us more evidence that for lower risk patients, treatment with thiazides doesn't seem to provide any additional benefits compared to the other treatment classes for reducing your chances of getting an acute myocardial infarction. Yeah, so this here presented only a small number of the results we have already generated, and still this is still a small fraction of the results that we can generate in general, because if we assume that we're going to extend this analysis in more databases. So you can come to my poster to see some more results, or you can go to this link here where I have uploaded all the results that I've generated thus far. Thank you.
Thank you, Alex, for a great presentation. Very important to indeed investigate treatment effect heterogeneity. Next speaker is Chen Yanover, PhD and a senior researcher at the KI Research Institute in Israel, where you apply causal inference and machine learning tools to healthcare data. You received a PhD in computer science and structural biology from the Hebrew University of Jerusalem.
Thank you, Katia. Oh, sorry. I want to start from the end and first thank all the collaborators who contributed to this study and tell you a little bit about IBD, inflammatory bowel diseases, which refer to 2 main diseases, ulcerative colitis and Crohn's disease. These diseases affect 1 to 2% of the population, and as they are typically diagnosed at early age, they cause lifelong effects on patients and families. And this study is actually, a first study in addressing these diseases in the, and as I know, in the OHDSI community, and trying to characterize the disease trajectories of patients suffering from these diseases. I'm presenting a multinational cohort study that at this point includes results from 16 different databases. Thank you. From 6 countries. When we defined the cohorts, we used diagnostics codes as well as prescriptions for IBD, ulcerative colitis, or Crohn's disease. And we extracted both predefined features per the feature extraction OHDSI package, as well as more than 100 IBD-specific features in different time windows before and after the onset of the disease. This is just small sample of a very tiny sample of the results that we obtained. So on the left-hand side, these are a set of histograms showing the Crohn's disease age at diagnosis in one specific database across different index years. So the bottom is early 2000s, and to the top row is actually 2020s. And as you can see, denoted by the stars, the age at diagnosis actually decreases over time. So this is one type of analysis that we are doing. The second one on the right-hand side, looking at hospitalization rate post-diagnosis with, again, Crohn's disease. And what you can see here is that in the both Asian databases from Japan and Korea, the initial hospitalization rate is actually higher than in the US. And interestingly, this is not a case for ulcerative colitis, where all databases have pretty much the same hospitalization rate a long time. Just 2 examples of the types of analysis we can run with the very large results that we obtained from all these databases. And I wanted to end by highlighting a few of the challenges that we faced during the study. Some of these were already mentioned in previous talks and maybe also addressed in community efforts. The first one is the challenge of context. So nowadays, it's not too complicated to run diagnosis or an analytics package across multiple databases. But the real challenge is to understand the result once you get them, right? Because in many cases, these are databases that you are not familiar with. They may cover different populations, and the way that healthcare is managed in each one of these databases may be different. So in order to make sense of the results, we need to be able to understand the context of each one of these databases. And I think that could be really useful if we have some resource where each database would be described both in terms of the population that it covers, but also in the terms of how healthcare, what type of healthcare system it covers, and how practically healthcare is managed in this database. The second one has to do with reproducing studies. So again, the community invested a lot of effort in building tools that allows rerunning the same study in different databases, different environments. But in some cases, you realize that there are additional aspects that may affect whether a study would be reproducible or not. One example is vocabularies that are actually updated a long time. And it may be that definitions of cohorts or features that are at some point in time extracts specific set of patients or attributes going forward change and do not cover these or not extract these set of attributes as before. The third challenge is the challenge of volume. So our study generated a large volume of data. We have 16 databases, and each one we define multiple cohorts, and we look at different strata along different time windows. That accumulates to a large amount of data. And it's not easy to view and handle these large amounts of data. And we may want to develop tools either to shrink this data to manageable size or to view and handle this data more efficiently. And the last one is actually a limitation of our study, and I guess other studies as well. We focus on binary attributes and do not extract statistics for continuous one, so no measurements, lab results, and so on. And we look at specific set of strata, but when we want to combine strata and get results for a more refined set of patients, this is currently unavailable. It would probably doing so will increase the size of the results even further, but in many cases that's interesting. I would like to end by thanking the community for building the tools that allow us to run this and other studies, and would be happy to discuss the study and everything around it in the poster session. Thank you.
Thank you, Chen, for your presentation, also addressing some of the challenges and limitations that you encountered. Last but not least, we have Ismail Gögenur, I hope I pronounced it correct, from the Center for Surgical Science in Denmark. Your biosketch was amazing when I read it. So you're a colorectal surgeon, founder of Center for Surgical Science, which is a multidisciplinary research unit involved in translational research and clinical research, big data methodologies. You have more than 450 scientific articles, and you're currently supervising more than 20 ongoing PhD students. And your research focuses on development and implementation of personalized medicine in oncology and surgical innovations.
Thank you very much for the honor of the podium. So the last presentation before lunch. I will hope that within the next 5 minutes I can convince you that using the OMOP infrastructure can actually result in a real-life benefit for patients that are scheduled for cancer surgery. So the approach and the understanding of what is the need out in the clinic is that if we look at our guidelines, it is providing the best practice at the current state of practice, which is a situation where I cannot really select between my patients with respect of what are their risk factors to ameliorate what is the reality, which is 1 out of 4 patients are getting recurrence of cancer after surgery, and almost every second patient are getting complications to oncological surgery. So this is the best practice. And what we need is to develop a better language, give us as clinicians some tools that we can incorporate, giving us a little bit better outset for providing good surgery and perioperative care. So the registries are obviously giving us a huge amount of benefit with respect of using retrospective data to find models that can provide us value on the right side of the slide. So if I knew what is the risk of my patient for dying within 1 year, for example, could I then implement an improvement in that care of that patient in order to prevent complications and improve outcomes? So 1 year mortality, in my view, is an excellent proxy for saying this patient has a high risk of getting some kind of side effect or complication to surgery. So what we did was to collect the Danish registries. These are national patient registry. This is the Danish colorectal cancer database. It's the Danish prescription database and also the Danish laboratory database, which provided us a data source of 77,000 patients with colorectal cancer with a data granularity around 60,000 covariates per patient, and also trajectory data from 40 years before diagnosis. So an excellent platform to do machine learning-based models that could be implemented in a team structure where we could use these data to say, okay, we want to approach your treatment in a different way than what our guidelines are telling us. The models that we have been presenting in our poster, and you're more than welcome to run by to get some of the details, are the ones that you can see here on 30 days mortality, 90 days, and 365 days mortality. Here are some event rates, our performance, the AROC for the 1-year mortality with good calibration, and also some differential outcomes according to what subgroup of patients that we were looking into. So you might say, okay, now we can publish a lot. We have created a clinical grade data source, a common data model. We can publish a lot, but I would really like to be putting this into clinical practice. So this is what we did. At 1st of February this year, we implemented a model that is giving us data regarding what is the risk of this patient dying within 1 year if we were to operate the patient according to our clinical judgment. So, is it below 1%? Is it 1 to 5%? 5 to 15 or more than 15% risk of mortality. So our surgeons right now, every day when we see a new patient, enter the 24 covariates into the model, and then we register this into the patient journal and provide 4 different clinical trajectories for the patient. So for those with the highest risk of mortality, we're doing a lot, and I cannot go into details, but we're prehabilitating, training the patients for 4 weeks, giving IV iron, intensive perioperative care, etc., all in order to improve outcomes. So I'll give you some of the data, and I think that I'm providing the smallest cohort result in this meeting, so I feel very humbled. But don't mistake, I'm very, very happy with what we have been showing. So for the first 80 patients since 1st of February, we have reduced the length of stay, we have reduced the morbidity, so the number of severe complications, and we have also a reduction in readmission after surgery. So you might say that this conclusion is valid, that we can use the OMOP-based common data model into clinical practice. And you might also say, so what? 80 patients, hooray for that. I would argue that it's extremely important, and also especially in this meeting and also in the future, to make a focus on these use cases where we can actually take, as Christian said before, the last mile before clinical implementation. So what we get out of these kinds of projects is obviously a clinical grade common data model. So what we are also doing are validating that the registry data that are retrospective data, when we validate that into a clinical implementation, we can actually see that when the surgeon is entering the data from the patient journal, so it's a different data source, we're generating exactly the same prediction, and we are having the same subgroup distribution as we have when we are looking into registry data. So it's extremely important proof of concepts that can be easily scaled into other patient categories. And I think that this is why I'm very much happy with this data infrastructure, because it also gives some scalability to other countries, and we have now started also collaboration with our Dutch colleagues and Norwegian colleagues to do federated learning-based models. So huge thanks to the amazing team at Center for Surgical Sciences, our collaborators, Eden's Health, and the 2 Ps that has been very, very big support during our journey. Thank you very much.